The next thing we're going to cover is how to create graphs that organize, summarize, and present your data. While it's possible to get a sense of the shape of a distribution when it is presented in table format, when the data are organized in a graph, the shape is very apparent. When we talk about shape, what we're looking for is how closely the shape of the graph approximates the bell-shaped curve. The bell curve is our primary reference point, and for any data set or distribution that is considered normally shaped, most of the scores will cluster around the middle range of values. That is what causes the bell in the bell-shaped curve, with fewer occurrences of lower and higher scores on either end. The graphs you're going to learn about are set up in a consistent format, with the data organized on two axes. On the vertical axis, you list the values that reflect the number of frequencies you have of each score in the X data set. On the horizontal axis, you list the range of score values that encompass all the scores in your data set. Let's look at an example. This is an example of a frequency distribution histogram. The same set of quiz scores is presented in the frequency distribution table on the right of the slide and in the histogram. A frequency distribution graph is basically a picture showing the information available in a frequency distribution table. We will consider several different types of graphs, but all start with two perpendicular lines called axes. The horizontal line is called the x-axis or the abscissa. The vertical line is called the y-axis or the ordinate. The measurement scale, the set of x values, is listed along the x-axis in increasing value from left to right. The frequencies are listed in the y-axis in increasing value from bottom to top. As a general rule, the point where the two axes intersect should have a value of 0 for both the scores and the frequencies. Then you list all the numeric scores on the x-axis and include those with a frequency of f equals 0. Draw the bars above each class interval, each x score value. The height of the bar corresponds to the frequency, and the width of the bar corresponds to real limits of the score value. So that is why the bars butt up against each other, because they are designed to show a half measure above and a half measure below. This next graph is called a modified histogram because it doesn't show the vertical axis on which we track the number of times a score occurs. The modification takes the form of stacked boxes, which show how many times a score occurs. So it still shows us that we had one occurrence of x equals 1, 3 occurrences of x equals 2, 3 occurrences of x equals 3, and so forth. A third graph that is appropriately used for interval or ratio data is the polygon. Here, instead of bars or stacked boxes, you place a dot at the intersection of the score, x value, and the number of times that score occurs in the data set. Then you simply connect the dots, extending the line on both sides to the previous and following score value so that the line intersects with the x-axis. If the measurement scale you used to collect your data was not based on an interval or ratio scale, but rather a nominal or ordinal scale, the appearance of the graph you create will be different. On the slide, a bar graph showing the distribution of personality types in a sample of college students is shown. Notice that the appearance of the graph is different because the bars don't butt up against each other. Instead, there's a space between them. This is done on purpose and designed to visually represent the nature of the measurement scale. Because personality type is a discrete variable measured on a nominal scale, the graph is drawn with space between the bars.